So let's look at a few properties of this scalar triple product that we have just learned after finding out how to actually carry out this operation, how to actually calculate scalar triple product of vectors given in various forms, how interchanges will affect the result of scalar triple product, what is the geometrical interpretation. After having seen all this, let's look at a few properties. Now, I would like to draw your attention to something. I guess I should have told this to you before as well, but nevertheless, let's look at this. Scalar product. If I have two vectors and I find their scalar product, what do I get as the output? I get a scalar, right? I get a real number. Vector product that we have seen. We calculate vector product of two vectors. If we calculate their cross product, what do we get as a return? We get a vector, right? We get a vector. That's why it's called vector product. What is this vector? This vector is the one which is perpendicular to the plane containing both of those vectors, right? What about scalar triple product? What is it giving me? Is it giving me a scalar as my output or a vector as my output? Just look at that. So I have a vector A bar, B bar and some C bar, right? If I want box ABC, then that means I have A cross B dot C. A cross B is a vector. And then I'm taking the dot of that vector with another vector C. So ultimately I'm calculating the dot. So what should I get? I should get a scalar, right? I should get a scalar. And what am I getting? What is this actually giving me? It is giving me the volume of the parallelepiped, right? So if my vectors are like this, then the parallelepiped will look something like this. So the volume inside this parallelepiped is given by this box ABC, and that volume is the scalar that I will get, right? That volume is the scalar that I will get. So I would like you to draw your attention to this, that in scalar triple product also, just like scalar product, in scalar triple product also your output is a scalar. It is a real number, because ultimately you're calculating the scalar product of two vectors, like in the end. So with this, let's move on to the first property, and that is the position of the dot and cross can be interchanged. So dot and cross can be interchanged. Now, this is not something that's very difficult to, or this is not something that we've been seeing this for the first time, because I've already told you box ABC is equals to A cross B dot C, or I can also write this as A dot B cross C. Also, I gave you the reason as to why this is true. So let's actually just look at it once again, because it's coming under properties. If I have three vectors A bar, B bar and some C bar like this, what is box ABC going to give me first of all? It is going to give me the volume of this parallelepiped, right? So this is the parallelepiped that will be formed using these vectors as the edges. So the volume of this is your box ABC. Let's look at what A cross B dot C is going to give me. So A cross B, first of all, A cross B is giving me the area of this base, the area vector of that base, and then when I dot it with C, that means I will multiply it with this C perpendicular, this edge, right? And when this area is multiplied with this C, I get the volume. And that's how I'm getting the volume of this parallelepiped. Let's look at the second expression. So for this second expression, what I will do is, I will use a different approach. For the second expression, you are first doing B cross C. So that means you are taking B and C as your base. So you are taking that as your base, and then you're dotting that with A. That means this A, the part of A that is actually the height to that, you're multiplying that area with this height. So even this base area into height, even here you will get the same volume. Even using this, you will get the same volume. So ultimately, you are getting the volume of this parallelepiped in both these cases. So that is the reason why both of them are same. So that is the reason why dot and cross can be interchanged. So remember that as a property. We've already seen this, but just for revision, just keep this in your head. It will be useful. Let's move on to the next property. Let's look at this next property. According to the next property, if I just put a k inside this box, I can bring that k outside provided that this k is a scalar. Right? What's actually happening here? Let's look at why I can actually bring it out. What's happening here? So this k into a bar actually is sort of a k a bar. This is also a vector. B bar, C bar. So this, you're taking the cross product of a bar, or for example, you're taking the dot product of a bars and k a bar with b bar and c bar. Right? Let's look at it as something like this. So when you had your parallelepiped initially, your edges were A, B and C. When you did box ABC for this, you got its volume. If you increase the length of this A bar to some K A bar, then what will happen is this parallelepiped that you see, it will slightly increase in length, right? It will slightly increase in length. From A bar, it will become K A bar. I can't say increase or decrease because that depends on whether K is greater than 1 or less than 1, but it will change by K A bar, right? So it will change by K A bar. Let me just, for explanation point of view, just let me assume that it has increased, right? So here, now this quantity is the volume of this new parallelepiped. So in a rectangle, in a cuboid, where your volume was LBH, if I change this L by some lambda times so that your cuboid becomes, the length becomes lambda L, then volume will be lambda LBH, right? Because this quantity will become lambda L. Similarly here, this quantity is become K A bar. So the volume also will multiply by K times, right? The volume also will multiply by K times. So that is what is happening here. This is the volume. This is the original volume. And that's being multiplied by K because one of your edges is actually multiplied by K. So that's what the property is. Let's move on to the next property. So this next property is a sort of a distributive property. So I would just like to give the name distributive property to it. So just like your dot product, your cross product, even your scalar triple product is actually holding this distributive property. And this property is not very difficult to prove because box A plus B, C bar, D bar, you can actually write this as, this can be written as A plus B cross C bar dot D bar, right? So A plus B cross C can be written as A cross C plus B cross C. Why? Because cross product is distributive. We've already seen this. And now you're dotting this with D. And now dot product is also distributive. So like this entire bracket, I can distribute this dot product to both these terms, right? Because even dot product is distributive. So this is A cross C dot D plus B cross C dot D. In fact, you should actually practice proving these by yourself so that your hands get used to the vector algebra, because the difficulty with vector algebra usually is that your hands don't get used to. So before writing every step, you just hesitate because this is not your normal addition or subtraction. So you just hesitate writing these steps and you just keep feeling that whether I'm writing the right step or not. So this is why you just need to, look at the textbooks and just derive them once by yourself, prove these laws once by yourself, and then you'll be good to go. So A cross C dot D, this can be written as box ACD, right? This can be written as box ACD. B cross C dot D can be written as box BCD, and this is what you had to prove, right? So this is the sort of distributive property for your scalar triple product. I would also like to give you an interesting note here, just useful from the exam point of view. If your box ABC is greater than 0, then it is called as a right-handed system. So A, B, C, in this order, if they are greater than 0, if the box product is greater than 0, then it's called a right-handed system. So sometimes they might just give you 3 vectors and they might just end up asking you whether these 3 vectors form a right-handed system or not. So what you have to do is, you have to take the vectors given in the order in whatever order they have given in the question, you have to place them in the same order, take their box product. If the box product is greater than 0, then they will be called as forming a right-handed system. With this, let's move on to the next property. And if I have just written this, so also box ABC less than 0 should be left-handed system. So if your box ABC is greater than 0, then it forms a right-handed system, and then if your box ABC is less than 0, it forms a left-handed system. Let's move on to the next property. The next property is extremely crucial from 3D geometry point of view as well, so pay extreme attention to the next property. So this property is an extremely crucial property, a very, very important property from the 3D geometry point of view. So this property says if I have 3 vectors A, B, C, so you can look at those vectors here A, B, C. If these 3 vectors are non-collinear, so first of all, your 3 vectors have to be non-collinear, because it might just end up being that, okay, if your A and B are collinear, then what is A cross B? What is A cross B if A and B are collinear? A cross B will be 0, right? Because they are along the same line, so the angle between A and B will be 0, and sine 0, you will get the sine 0 term from the cross product, so that will make this entire thing 0, right? So that's why I'm mentioning this, that okay, your vectors have to be non-collinear, right? So A, B, C are 3 non-collinear but coplanar vectors. So the A and B, A, B and C are something like this. They are not along the same line, but they are in the same plane. If they have to be in the same plane, then their box product has to be 0. Let's look at why this is true. So let's evaluate this expression. Box ABC can be written as A cross B dot C. So A cross B means I have to take the cross product of this A vector and B vector. So what I will do is, I will bring this B here and I will join it with A. Right, I can always do that without changing the magnitude and direction. If I bring a vector from one position to another, it will remain the same vector, right? So this is my B bar. A cross B, if I actually calculate A cross B, that means I will have to put a screw here, rotate from A to B through the smaller angle, and that is going downwards, right? So A cross B is a vector pointing downwards, and its magnitude is obviously AB sine theta, where theta is the angle between A and B. So this is 90 degree to this plane. So this is 90 degree to the plane. But C is in that plane, right? Because I'm already saying that A, B, C are coplanar. That means your C is in the plane. So your C is, if I just move this C from here, and I bring it here at this junction. What is the angle between A cross B and C? It is 90, right? Because C is in the plane and A cross B is perpendicular to the plane. C is in the plane and A cross B is perpendicular to the plane. So the angle between this vector A cross B and this vector C is 90. And I am taking the dot product. What is the dot product of two perpendicular vectors? If A is perpendicular to B, then what will A dot B be? It will be 0, right? Because you will get a AB cos 90 term. And this cos 90 will make it 0. Similarly here, A cross B is perpendicular to the plane containing C, and C is in that plane, right? So obviously angle between these two is 90, so this has to be 0. Imagine if your C was not in the same plane. If your C was not in the same plane and something like this, it was pointing outside, then this angle would have been non-zero. It would have been some theta, and I would have some A cross B mod C sine theta term. Cos theta term, right? Because I'm taking the dot product of A cross B and C. So I would have this cos theta term. But the moment C comes in the plane, this cos theta becomes 90. This is the reason why if three vectors are collinear, are coplanar, and obviously they have to be non-collinear. Why am I mentioning non-collinear? Because if they are collinear, then this cross product itself will become 0. Whether this C is in the plane or not will be immaterial, right? It will not matter at all, because this A cross B itself will become 0 if A and B are collinear, if two vectors are collinear, right? So you have to make sure that your vectors are non-collinear, and then if they are to be coplanar, then their box product has to be 0 for that, right? And the reason I've explained you. If you look at this, you have already seen this before. You've already seen this before when I was explaining you linear combination of vectors. There we saw that three vectors, if they were in their component forms, so let me use a different color. If three vectors were in their component forms, something like A bar is equals to A1i plus B1j plus C1k is a vector. B bar is equals to B1i plus B2j plus B3k is a vector, and this is, I wanted to write A1i, A2j and A3k, and C bar is your C1i plus C2j plus C3k. So if these three are your vectors and they are obviously non-collinear, if all these three are non-collinear and they are to be coplanar, then this determinant had to be 0. B1, B2, B3, C1, C2, C3. You have seen this property. If these three are to be coplanar, then this property should hold good. Where was this coming from? It was coming from this only. It was coming from this. Because you've already seen what is the box product of ABC. What is the box product of ABC? If ABC are in their component form, then how do you calculate the box product? Box product is calculated using this determinant, right? It's calculated using this determinant. This particular determinant. I've already shown you this. Now what I'm saying is, if ABC are coplanar, then this scalar product has to be 0. And scalar product is this determinant. So this determinant has to be 0, right? So this property that you have seen before there, I told you, you will actually encounter this when we study scalar triple product. Not just here, in fact, you will also encounter this in 3D geometry. In fact, in 3D geometry, you will use this result. So this was an extremely crucial property. I hope you have understood this. Let's move on to the next property. So this final property is extremely simple. It simply says that if a box product has two repeating terms, it will simply become 0. The box product will simply become 0. What is the reason? Because if you actually calculate A cross A dot B, when you expand this, you will get A cross A dot B. This A cross A term will be 0. So ultimately you will get 0. So in a box product, if you have three terms, and if any of the two terms repeat, if any two terms repeat, or any two vectors I should say repeat, then box product becomes 0. In fact, all of this can be thought from the geometry point of view also, both your previous property and this property. So previous property said if A, B, C are in the same plane, then box product has to be 0. If you think from the geometry point of view, what is box product giving you? Box product is giving you the volume of this parallelepiped, right? The volume of this parallelepiped. If this C bar lies in the plane of ABC, so A is something like this, B is something like this, and if your C is in the same plane, then there will be no parallelepiped formed at all, right? So this thing has become flat on the floor. There is no parallelepiped formed, so the volume will be 0. That is the reason why in the previous property it was 0. The box product was 0 for three coplanar vectors. Even here, if you see, if two vectors are repeating, so if your B and C coincide, for example, if two vectors are repeating, then let your B and A coincide. So your first vector is this, your second vector is also this. So once again, using A and C, you are just getting a parallelogram. You are not getting a parallelepiped, because for a parallelepiped, you also needed that edge. You also needed this edge, right? And that's missing because two edges are repeating. So there is no parallelepiped form, so the volume has to be 0. Even from the geometry point of view, you can give yourself that explanation. So with this, we complete all the properties of scalar triple product from all angles that we had to. And in fact, with this, we complete the scalar triple product concept itself, looking at it from all perspectives. Let's move on to vector triple product.